All right. Determine the hydrogen concentration and whether the solution is acidic, basic, or neutral for the following. So let's make sure we know how to do this. If we have a hydroxide ion concentration, this is easy because there's no, you don't have to figure out what dissociates or anything like that like you do down here. So I'm telling you that the hydroxide ion concentration is 0.000250 molar. How do I go about calculating the concentration of hydrogen? Okay. Well, I know that Kw is always the same, and I know that hydroxide times hydrogen concentrations is equal to that Kw, which is 1 times 10 to the minus 14. So then I write down what I know. I know this, and I know Kw, and I just rearrange and I solve for H. Okay. Same thing down here. Now, in this case, if you write these things out, you can tell by looking already whether it's acidic or basic. Like if you would have wrote that in scientific notation, you would have had 2.5 times 10 to the minus 1, 2, 3, 4. Okay? And we know like 1 times 10 to the minus 7 is our neutral point. So if we look at this one, 10 to the minus 8, is that less than or more than a normal neutral solution? Less than. So we've got lower amounts of hydroxide than a neutral solution. That must mean we're going to have higher amounts of hydrogen, right? So if you have a higher amount of hydrogen than normal, less amount of hydroxide than normal, what do you got, acid or a basic solution? Is that solution acidic or basic? You've got less than normal hydroxides, less than normal. Remember, hydroxide makes the base. You've got less than normal hydroxide. That must mean you're going to have higher than normal hydrogen. So if you've got more hydrogen than you do hydroxides, do you have an acid or a base? You've got an acid. Okay, this is an acidic solution. All right. So if we know this, here is our hydrogen ion. We're solving for this. We know that Kw divided by the hydroxide is going to give us our answer. So here's our hydroxide concentration. There's Kw. Work it out. You've got 4 times 10 to the minus 11. That's obviously much, much less than the amount of hydroxide that you had. So that means you've got a lot more hydroxide present. That means you've got a base. Okay? Even if it's a very weak, it doesn't matter. It's a basic solution. That means if you test the pH, it'll show up as a base. Okay? A basic solution. Do this one. Do the same thing. We solve for hydrogen. Take 1 times 10 to the minus 14 divided by 3.5 times 10 to the minus 8, and you get 2.86 times 10 to the minus 7. Now that minus 7 is deceiving because the exponent now looks neutral. So now we've got to look at the actual number. Remember, 1 was what we were looking for. So now it's a matter of, is this going to be higher? Is 2.86 times 10 to the minus 7 higher, of greater value than 1 times 10 to the minus 7? And the answer is, of course, yes. Right? Or we can just look, either way you want to look at it, let's compare our acid level to our base level. 2.86 times 10 to the minus 7, 3.5 times 10 to the minus 8, which one of those is bigger? This one, right? So that means you have more hydrogens present than you do hydroxides. Therefore, if you test the solution, it will test moderately acidic. If you test its pH. Okay? All right. Take a look at calcium hydroxide. Now, there's an extra step involved with this because I don't give you just hydroxide ion concentration. I give you the total concentration for calcium hydroxide. So what you've got to do is do what to the concentration? You've got to double it because there's 2 hydroxides that will come out for every one of these that dissociate. So we take that 2 times 0.20 to get 0.40 molar. Then we do the same thing we just did. Okay? If that's the case, we divide, we get 2.5 times 10 to the minus 14. How does that compare to our hydroxide ion concentration? Obviously, it's much, much less, right? That's an actual 0.4. This is 2.5 times 10 to the minus 14, a bunch of zeros, way over here. That's a really small number compared to that. So that means there's a whole lot more hydroxide ions around than there is hydrogen ions. Therefore, it's going to be basic. Okay? Follow that? We'll see. Okay, now, the pH scale. When we look at the, I'm going to bring in that in a second, but if we look now, pretend like this was a pH scale. I'll show you where those numbers come in a second, but here's 10 to the minus 7. Remember we said that here's our hydroxide ion, or sorry, our hydrogen ion concentration. Here's our hydroxide ion concentration down here, and we said that at neutral, that means about where there's the same amount of hydrogen and hydroxide present, there's 1 times 10 to the minus 7 moles per liter of each, right? Multiply them together, you get 1 times 10 to the minus 14. Okay, to visualize what's happening here, we know that as the hydrogen decreases, right, in order to keep the same value, you've got to proportionally increase the amount of hydroxides. And the same goes true in the other direction. As this number, remember this is increasing, going from a -7 to a -5 to a -3, that's actually getting bigger in terms of its value. It's just that it's very small because the amount of these things dissolved in water are very, very small, right? So as this continues to increase in concentration, the hydroxide will likewise decrease in concentration. And you will find the same thing at this point, at this pivotal point where everything is sort of neutral. There's the same amount of both present. Once you start to tip those scales, that's where you get acid-base. Notice that as soon as the hydroxide ion concentrations start to get larger than the hydrogen, you get solutions that are basic in nature. And likewise, in the other direction, when things start to tip the scale and become more hydrogens present than a hydroxide, you start getting acidic solutions. Naturally, things that are way down here are very strong acidic solutions versus the things that are way over here. Okay? Now it says, even though it may look like it, neither hydrogen ions or hydroxide ions will ever be 0, because 10 to the 0 is 1, right? You're not going to get, because of the dissociation of water, that's not going to happen. Now, you can have greater than 1 molar concentrations for other things, okay, that are out there, like sulfuric acid 12 molar, nitric acid 18 molar, hydrochloric acid 12 molar. These are very, very concentrated acids. 1 molar is the theoretical end here of what we're talking about, because we're talking about water, and we're talking about the hydrogen and hydroxides that come apart in water. So that's very, very weak compared to all the other stuff. That's why our scale's cut off here. Okay. All right. Now, the pH scale is actually a logarithmic scale, and what you see here is a logarithmic scale. What do I mean by that? I mean that these steps are not just one value at a time. Now think about it. If I go from 1 times 10 to the minus 2, how do I write that in decimal form? Okay, 0.01. And then I look at 1 times 10 to the minus 3. How do I write that? 0.001. Now, what factor of an increase is that? When I go if I move up from 1 times 10 to the minus 3, which is this, and I move up to 1 times 10 to the minus 2, which is this, if I took this divided by this, what would my answer be? How many places did I go? What does each decimal place represent in our scale? A tenth, right? So a factor of 10. Each step on this scale from 1 to minus 2 to minus 3 to minus 4 is not just one number step. It's actually a factor of 10. So if you measure something that the pH is 7 and something else that the pH is 6, it's only one number, but it's a huge difference. It's 10 times the difference in concentration. Okay? So if something has a pH of 4 and a pH of 3, whatever the pH of 3 is actually 10 times stronger than a thing that's pH of 4. pH of 2 would be how many times stronger than a pH of 4? See, that's the thing. Every step is a factor of 10. That means you multiply by 10 every step, right? So it would be 100 times. So it doesn't seem like a big difference between 2 and 4, because when you subtract them, you get the number 2. What does that mean? It's a logarithmic scale. There's huge jumps here. From 2 to 4 is actually a 100-fold increase. And then from 5 to 2 would be a 1,000-fold difference in terms of the concentration. A pH of 2 is 1,000 times more acidic than something with a pH of 5. So decimal numbers, 2.2 versus 2.1 in pH, it's a big difference, okay, in terms of concentration. So we're looking for narrow ranges here.